Okay, we're going to start a series of talks on the VMS thematic program, and Octavio is going to start us off, and I apologize for the typo on the agenda for your name.
So, afternoon everyone. I'm going to talk about the geochemistry that we've been doing on the Blake River group and then the Stoughton-Roquemaure assemblage, and for the implications on the BMS endowment. So my name is Octavio Vite-Sanchez. I'm a PhD student at NRS. So I imagine you have seen enough this image, but just to remember a little bit of the Abitibi. We have 7 volcanic assemblages subdivided mainly on geochronological constraints. So, why do we pick the Blake River and the Stoughton-Roquemaure? Because they represent the extreme poles or BMS enrichment and BMS poor endowment. However, we can observe here Blake River only represents 11% of the surface area, whereas for the Stoughton-Roquemaure it represents almost a third. So what are the research questions for this project? Are there compositional variations in space and time that correlate with BMS fertility? Can we see these variations at the scale of Abitibi between assemblages and within assemblages? So can petrogenesis explain the differential BMS endowments? So in order to address those questions, we have compiled an extensively the geochemical database of subalkaline volcanic rocks. We categorize these rocks based on immobile elements. Then we conduct a comparative analysis between the BMS endowment and BMS poor assemblages. And in order to understand what is the geochemistry of these rocks, we are doing petrogenic modeling using the magma chamber simulator. So these are the samples that we have compiled for the Stoughton-Roquemaure. We have over 1,000 samples. The Stoughton-Roquemaure is represented here by this pale green. Then for the Blake River, we represent the Blake River only with the Blake River group. So as you can observe here, so we have almost a double in terms of number of samples. So what are the first order subdivisions that we've been doing? So first we want to subdivide the rocks in terms of compositions. For that for separate ultramafic composition, we use the Jensen plot. Then for mafic, intermediate, and felsic, we use the Pierce 96. And for the magmatic affinity, we use the Ross-Bedard plot. Then, so how we analyze the data. So for that, we use a principal component analysis technique. And in this PCA, we throw a bunch of elements that we think that are the most meaningful in terms of petrogenesis, but they are also immobile. So here we have already formed the groups, and we're going to see that in a minute. But what I want you to take from this image is that what are those elements that are causing the biggest variation in our data. So, and that is titanium, ytterbium, and thorium. So with that in mind, we create this diagram. You've seen both data for the Stoughton-Roquemaure and for the Blake River. In circles, filled circles, we have mafic compositions, intermediate compositions, non-filled circles, and then for felsic, we have these diamonds. So we are going to see details of the groups through the presentations, but let's see first how they are the distributions on in each side. So for the Stoughton-Roquemaure, we have comatites that doesn't occur in the Blake River group, and here we have to notice what are the two most common geochemical groups. That is tholeiitic basalts and high thorium basalts for both cases. For the case of the Stoughton-Roquemaure, we have more of the tholeiitic basalts. For the case of the Blake River, it is the case we have more high thorium basalts. We have a rise in the medium thorium basalts. Then for the transitional compositions, They are not so abundant on the Blake River, but they have a rise on the Stoughton-Roquemaure, especially for the calcaline intermediates. Then when we go for felsic compositions, we kind of see the similar, the same geochemical groups, but it is the case that for the Blake River, the transitional felsic compositions tend to be more abundant. And for the Stoughton-Roquemaure, we have a rise in calcaline felsic compositions. So how does this group do in other diagrams? Here we have the Arrowwall 2008 that use several elements on a linear discriminator. So we can observe mainly the two major groups. For the tholeiitic basalts, they are typically on the morph field, and the high thorium basalts tend to go into the island arc basalt. And we can see a similar behavior for the Pierce 2008 that has been updated in a 2021 paper. And we see the similar behavior going from the mantle array to the island arc basalt array. So the characteristics of these groups for the tholeiitic basalts, tholeiitic basalts are typically have these flat profiles, low thorium niobium compositions. Then when we go for medium thorium basalts, they start to rise the composition in lighter earths. We start having this niobium anomaly, negative anomaly. Then when we go to the high thorium basalts, so these guys tend to have bigger niobium anomalies, higher concentrations in thorium and lighter earths. So we have a more like a steeper profile for this geochemical group. Then for the intermediate compositions, we have something similar. For the transitional, niobium anomalies tend to be lower, but when we go to the calcaline, the profile tends to be steeper, niobium anomaly really high, and high concentrations in thorium and lighter earths. So then when we observe the felsic groups on both sides, let's focus on the two first. So we have the tholeiitic felsic that is not really abundant on the Stoughton-Roquemaure, but we see something on the Blake River. They have like a flat profile, very similar to their tholeiitic precursor. But when we observe these high iterbium felsics, they tend to have a similar concentrations on the heavies, but we gain this concentration in lighter earths. So how these guys plot on the Hart 2004 plot, these guys tend to plot here on the bottom. So then for the transitional felsic and low iterbium felsic, that transitional is particularly more abundant, the Blake River, but they tend to have a similar profile. The only main difference between the low iterbium, this orange, and the transitional felsic is the thorium-iterbium ratio tend to be a little bit higher. And these guys tend to plot between the F4 and F3. There is where much of BMS mineralization on Noranda, for example, is occurring. And then for the calcaline felsic, these guys tend to have a steeper profile. Again, high concentrations in thorium and lighter earths, and these guys tend to go to the F2 and F1 field. So now for the fun part, the modeling. We have tried to model three different processes. One is the fractional crystallization, the other is the simulation fractional crystallization, and the other is the magma mixing. In this case, we are modeling how a felsic melt might modify a mafic melt. And in this case, we are always modeling an initial composition that is similar to tholeiitic basalt. In this case, the felsic melt and the wall rock is a TTG average composition. So before going into the fractional crystallization models, I wanted to show you what is the distribution of this on the major elements of the groups. In this case, I'm using the Stoughton-Roquemaure data, and we're using the less altered samples. In this case, I want you to put your attention on the tholeiitic basalts. These guys have the high concentration in magnesium, well, after the ultramafic compositions, that these guys might go to 25% in magnesium. But most of the bulk of the compositions occur here in this zone of magnesium. So tholeiitic basalts tend to go to low concentrations in titanium to high concentrations. It is the same case for the iron. Low concentrations alumina a little bit, they rise a little bit, but they tend to have similar concentrations in silica. And then for the other case, the high thorium basalts, they tend to be lower in titanium and iron. They tend to have more silica and also more alumina. So for the fractional crystallization models, we want to establish first what are the pressures or the most common pressure that we might observe. So for one of the cases that we use here, it was anhydrous tholeiitic basalt. Normally these anhydrous tholeiitic compositions tend to have a gain on iron and titanium. So we submitted to different pressures, as you might see here, 1 kilobar to 20 kilobars. You can see the estimated pressure on the right, depth, sorry. And we can observe how these gains on iron and titanium are typically observed between 1 and 5 kilobars. Then for the rest of the pressure, we don't gain that, and we don't have a good behavior in terms of silica for this tholeiitic. So we are confident that we are in a zone of middle to upper pressures. So for the rest of the modeling, we are going to use the 2.5 kilobars pressure. So this is the case of the Blake River. This is the work that we already published recently. So we can see the case here for the anhydrous composition, these filled solid lines. When you are having low water concentration, you gain these enrichments in iron and titanium, low concentrations alumina. But then when you add water into this magma, you can go to lower concentrations. And we can observe how that more, let's say, water-rich magmas tend to be on this lower side. And we can observe also that for the other groups, because when you have an assimilation, an AFC process when a TTG, you can modify the fractionation lines, as you can observe this with these dotted lines. So let's see how that affects the trace elements. So I want you to focus here on the tholeiitic basalts and the intermediate tholeiitic compositions. So if we are fractionating that magma, the line must go horizontally here. So we have the model here, the initial composition, and then we start fractionating that magma. We can obtain to 80% of fractionation that andesitic composition. And to compare, we can observe on the right the average composition of each group. We can observe how we achieve that modeling. So how this affects when you are observing an AFC model. Here in the lower part, you observe the tholeiitic basalts. Here, the initial composition, and we have the wall rock. So when you're having an AFC process, that means that you are simulating the wall rock, but at the same time, you're fractionating the system. So in this case, when you simulate the initial composition, 1% of the wall rock, you might go to these thorium and terbium ratios. And you observe here how the extended trace profile has been modified. And I put here on the right the medium thorium basalt group average on green. So we might observe how that is kind of similar. Then when we go for the high thorium basalt, that means that we assimilate 2.5% of the wall rock, and the system has evolved to a basaltic andesite. You see the example here of the 2.5, and how that is very similar to the high thorium basalt group average. Then when we already assimilate 16% of the wall rock, the system has evolved now to an andesite. And this is the profile, the resulting profile of that, and we can see how it's similar to the calcalkaline intermediate compositions here. And we can observe that also in other discrimination, well, geochemical diagrams like Pierce, how these guys could go into this part, into the island arc basalts. So now we will see the mixing models. That is something interesting that we are start taking a look. So it is the same case. We are having the toleric initial composition being mixed with a TTG melt. So we have the temperatures for both. The TTG melt is for sure colder. So we have different proportions of the melt going into the toleric basalt. So we have the 1 to 10 example, that is the red line. Then we have the 1 to 2 and 1 to 1 comparison. So the result of that mixing, it is circled here with this red circle. The rest of the line is the fractionation of that mixing result. So we can see how we jump when we add the same amount of mass from the TTG melt that goes right to this composition. So that changes dramatically. The composition goes to more or less intermediate compositions. So we observe also what happened in this process on the trace elements. So we have the same models that I show, 1 to 10, 1 to 2, and 1 to 1. On the bottom, we observe the toleric basalt, and the first line just above is the resultant of the mixing result. So you can see how when you have more TTG melt going into the system, you really change that extended trace profile. So we can observe also that on the diagram that we've been talking, the toleric basalts, when you only add 1 to 10, 1 to 2, and 1 to 1 comparison. So we create these jumps, some compositions. And then the rest of the fractionation might help us to understand potentially what is happening with the more felsic groups. So just observe what is the distribution of the thorium-yttrium ratio that we thought is one of the most important causes in this variation. We can observe this on the Stoughton-Roquemaure assemblage. We can observe how they are mostly distributed on the center parts, as you can observe here, really dominated by this toleric basaltic group. It is also the case that komatitic basalt, well, all the komatitic ultramafic magmas are occurring on the central parts. But then we see an influence on the northern parts of the Stoughton-Roquemaure that is being indicated by this thorium-yttrium ratio is being higher in certain parts. Here, when we have the only BMS deposit, it is sit around here, we don't have that high thorium-yttrium, they tend to be more intermediate. And we observe the Strat deposit over there. So we can also check the zirconium titanium distribution in the Stoughton-Roquemaure. It is dominantly mafic, but when we see the Strat deposit, we see some kind of fractionation that might be biased because the sampling on the felsic rocks around this deposit. So recapitulating, what are the characteristics of each site? So for the Stoughton-Roquemaure is being in place in 3 million years only. The Blake River has been in place in 9 million years. And the surface area that Stoughton-Roquemaure covers is a third, the Blake River 11 approximately. So we can intuitively think about the volcanic eruption rate. So for the Blake River, it has to be high, and for the Blake River, tend to be low to moderate. So we already checked the BMS tonnage for both. We have comatite for the Stoughton-Roquemaure, not for the Blake River. The felsic rocks tend to be more rare on the Stoughton-Roquemaure. For the Blake River, they tend to be more common. So we have the crustal interaction that we could see in both cases for the Stoughton-Roquemaure tend to be low to moderate, but for the Blake River, moderate to high. So the tectonic setting for the Stoughton-Roquemaure could be plume related, and for the Blake River group, it is uncertain. So now we are going to check what are the petrogenesis that we are thinking about the formation for the Stoughton-Roquemaure petrogenesis. This sketch is not to scale, so we suggest this plume origin for the Stoughton-Roquemaure. The central parts we observe these tholeiitic basalts, all the comatites occurring in the central parts and the south. But then for the north side, you remember we tend to observe more interaction with the crust. So in this case, we propose two processes. One that is but for this case, we need to have the TTG generation in the mafic lower crust to generate those TTG melts that might be mixed on the crust. And the other case could be also the AFC, that a tholeiic magma is being stored on the crust when you could have a AFC. However, we like a little bit more mixing because it is the case that you don't have too much of this composition here, like intermediate, the medium thorium basalts. It tends that we have a majority of these compositions, and the easiest way to go from here to here is doing a mixing. So to create these jumps in thorium ytterbium, and then we might have a crystallization of those magmas to explain the felsic compositions. Then for the case of the Blake River, it is a little bit more complex in this case, but we don't know if there's still a plume over there, but we put it there. So in this case, we have kind of similar processes occurring, but it is the case that the Blake River is the last of the volcanic assemblages. So it could be the case that the crust has been thickened because the pile-up of the previous assemblages. So the crust, it is potentially thicker over there. That might be helpful to create all these processes that we are thinking. That is, AFC could be more common over here because AFC create a differential composition that you could observe that goes here. You see a lot of these type of compositions, a lot of high thorium basalt, not so much of these guys, but this might create all this range in terms of compositions. Could be the case we also are having mixing. At the same time, we need this TTG generation. But another thing that we observe for the Blake River is that we are having this storage of magmas on the crust to generate fractional crystallization melts or products. That is the case here. We can observe it for the tholeiic basalt. So you are having those magmas, you fractionate it to intermediate, and you could even have more felsic composition of that same parental magma. So what are those processes that enhance the BMS? So one of the recent ideas that we've been thinking about is that for the case of Stoughton-Roquemaure, we talked already about these differences. The Stoughton-Roquemaure has been displaced really quickly. So it doesn't have the chance really to interact with the magmas on the crust. Then for the case of the Blake River, it is the case that has 9 million years time span. So, and you also have thickened the crust because of the previous volcanic assemblages. It is the last one. So you have the chance to thermally mature the crust because you might be injecting magmas into the crust that are being stored in middle magma chamber, let's say, that might modify all these isograds temperature that might be rising. So more recent numerical models suggest that in order to have this thermally mature crust, you need at least 4 million years in order to have that. So if we are observing that, we have more chance to storage those magmas on the middle crust, generating all these processes of AFC or mixing that could be feeding even the subvolcanic intrusions that we can observe or that could be necessary for the BMS generation. So, conclusion, the Stoughton-Roquemaure and the Blake River contain many of the same geochemical groups, but in different proportions. Comatite-tolite association on the Stoughton-Roquemaure suggests a mantle improved involvement. The Stoughton-Roquemaure in place quickly, has a more limited interaction with the crust, whereas for the Blake River it was in place slowly. We have more evidence for crustal interaction where we can observe these AFC or magma mixing processes. So this means that the upper crust, it is hotter, that is a good environment for the felsic magma generations and at the same time for BMS formation. So just a little bit of the future work. We want to submit this paper of the Stoughton-Roquemaure petrogenesis, finish and submit a paper about the chemical difference between Stoughton-Roquemaure and the Blake River group and the BMS endowment implications. And for me, it's finishing my PhD, and then Kieran will continue with the work in this project. So, thank you.